In chapters 10 and 11, we learned to describe a data set or a distribution graphically. Now we're going to talk about describing distributions with numbers. So describing a distribution numerically. We're going to first talk about measures of center, and then we're going to talk about measures of variability. What do we mean when we talk about measures of center? Well, another way to say that is measures of location. And what do we mean by location? We mean if we were to look at a histogram of the observations, where would the histogram be located on the real number line? So we mean where is it located on the real number line? So let's work with an example first, and let's look at this histogram on the right. What type of graphical display is this? Well, we've already ruled out that it's a bar graph, so we can cross out C and D. Now, how did we know that this wasn't a bar graph? Well, bar graphs have the bars denoting categories, categorical variables. That is simply categories. Our data on this horizontal axis is numbers. The bars touch, and on the horizontal axis, it's denoting a continuous distribution of numbers, and so this is a histogram. How do we determine whether it's a frequency versus a relative frequency histogram? Well, we're lucky here because it's labeled frequency. So we know it's a frequency histogram. Now on homework or an exam, I don't have to label it frequency for you to be able to tell me the difference. How are you going to know whether you're looking at a frequency or a relative frequency histogram if I mark out that label frequency? If it's marked out like this and you have no idea what it says there. Well, let's take a look at the vertical axis. So this goes from 0 to 100, so it could be frequency or relative frequency, because relative frequencies add up to 100%. How are we going to tell whether these are relative frequencies or frequencies? Well, we have one bar that's over 100 tall. The height of it is over 100. So clearly these bars don't add to 100. They add to way more than 100. That is a dead giveaway that this is a frequency histogram. The heights of the bars represent the number of people within each height range on the horizontal axis. So the heights of the bars in a frequency histogram add to the sample size n. There are this many people between 58 and 61 inches, and this many people in the next height category, etc. What are they going to add to in a relative frequency histogram? The heights add to 1 or 100, depending upon whether it's in decimal or fraction notation or it's in percent notation. So the heights add to 1 or 100 in a relative frequency histogram. Perfect. Now let's talk about different ways to think about measures of center. We're going to think about 3 different descriptions at the moment. If we were to fill up this histogram with solid material and balance it on a fulcrum, what would be the balancing point? Where would we put that fulcrum so that this thing balanced? Well, I'd say it'd be somewhere right in there, maybe a little bit to the left. Again, we're not trying to be very precise right now, we're just trying to get you to think of different ways of measuring the center of a distribution. So let's call the center, the balancing point, about roughly 68 inches. Just eyeballing it. Another thing we want to think about is the value that divides the upper half from the lower half of the data. We're going to call this M. Now this is really difficult to tell from a histogram because we don't have the actual data values. A stem plot would make it possible to do that since we have the actual data values. A histogram doesn't, since we bin together several heights in each category. So how are we going to determine this middle value? Well, we really can't from this picture, but the point was to get you thinking about what the middle value is. That is the height that has half of the people below it and half above it. So it's somewhere between 65 and 70 inches. And another thing to think about is which set of values occurs most often. Well, the highest bar here is the one representing 64 to 67 inches. So these are all different ways that we want to start thinking about data sets. Let's formalize what we just thought about. The first measure of center we're going to talk about is the median. The median is the one we're going to denote by the letter M, the capital letter M. This is the midpoint of a distribution, the number such that half the observations are smaller and the other half are larger. For the class height distribution from several semesters ago in Stat 110, there were 380 observations. This was a large class, and the median height was 66 inches. That means that half the class was shorter than 66 inches and half the class was taller than that. How do we find the median? Well, for a large data set like the one we're working with, we'd want to use a computer, of course. But what's the computer doing? It's arranging all the observations in order from smallest to largest, and then continuing the algorithm. If the number of observations n is odd, then the median is the center observation in the ordered list. Think about it. If we have 5 observations, we have 2 on the left and 2 on the right and 1 in the middle. So when we have an odd numbered data set, there is actually a middle value, and that will be our median. If you have an even number of observations in your data set, then there is no middle value. If we have 4 observations, there are 2 on the left and 2 on the right and none in the middle. So what do we do to handle this? We're going to take the average of the middle 2 values. Let's do an example. The first example we're working with is the distribution of home runs for Mark McGwire's reported seasons. Step 1 is to order the observations, and we've done that for you here. Step 2 is to determine whether the number of observations, that is the sample size, even or odd. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 observations. So we have an odd number of observations, n equals 13. So now let's find the median. Well, we have an odd number of observations, so there's going to be a middle value. And if 13 is our sample size, then there are going to be 6 values on the left and 6 values on the right of the median. So the median is 39. So 39 home runs is the median value of home runs. That is, half the seasons he had more than 39 home runs and half he had less. The mean is our second measure of center we're going to talk about. This is the simple arithmetic average that you're accustomed to computing. You add up all the numbers and divide by the number of observations. The mean is the one we can think of as the balancing point in the distribution. This is the one we can imagine if we fill up our histogram with solid material, it would balance the histogram. The mean for our class height distribution that we're working with is 66.803 inches. So the average height in the class during that particular semester was 66.8 inches. The notation is going to be the name of our variable. We're going to call ours x in this case. Sometimes we use the letter y with a bar over top of it. And we read this as x bar. So it's literally the name of the variable x or y with a bar on top of it. Computing the sample mean is simply adding up the observations and dividing by n. Written in mathematical notation, it looks like this right-hand formula, where x sub 1 is the first observation in our data set. It doesn't matter what the order of the observations is here. We don't put them from smallest to largest because we're just adding them all up. It doesn't matter which one we punch in our calculator first. So we take our first observation plus our second one, all the way up to the nth observation, and then we take that sum and divide it by n, our sample size. Working with our Mark McGuire home run data, we're going to compute the sample mean. The sample mean is x bar, and we simply add up all of our observations in the numerator. So 9 plus 9 plus 22 plus I hope you don't mind if I don't write out all these numbers, all the way up to 70. So you punch all the numbers in the data set on up to 70 in your calculator. We have them in order here, but notice again, they don't need to be in order. It doesn't matter which way you add them in your calculator. Divided by our sample size, which is 13. And when you do that calculation, make sure you're practicing that so you know how to punch it in on your calculator. You should get 39.92 home runs. Two things to notice here. First one is that the mean, and the median for that matter, get units. Here we're talking about home runs, so that's our units. It might be inches, it might be feet, it might be home runs, it might be days, it might be seconds. The second thing to notice is, hey, we can't have 39.92 home runs in a season, so some of you may want to be rounding this value up to 40. We're not going to round the mean or the median. This is because, think about the mean. It's the theoretical balancing point in the distribution. It doesn't necessarily need to be an achievable value in that distribution. It is the theoretical balancing point in the distribution. So we don't round the mean. We also don't round the median when we're averaging the two middle values. The last measure we're going to talk about is called mode. The mode of a data set is the most common value of the data set. There isn't always a mode of a data set, and sometimes you can have more than one. The mode is really handy because it can be used for quantitative data, like the mean and the median, but it can also be used for qualitative data. Qualitative is another word for categorical, qualities. So when you're talking about car color, for instance, you might talk about the most common car color. That would be the mode of a data set. So it can be used for quantitative data or categorical data.